right, is this looking a little bit better to folks? Less of a lag?
Yeah.
Okay. All right. So sorry about that. I have the router in my room, but sometimes it just isn't behaving well. So, okay. So back to the sine trig substitution. So when we look at this structure, it's important to know that A and B are both constant, okay? So whenever we see a situation like this, so the square root of a number minus x squared, then what we can do is rewrite it using this substitution, okay? So A over B sine theta, everywhere we see an x is gonna help us with getting the integral into a form that we can integrate, okay? Now, I just want to clarify a few things. Most of the questions that we're going to be looking at, the b value is going to be 1. Okay, so that's why for a lot of the questions it was like 9 minus x squared or 25 minus x squared, and there wasn't a number in front of the x squared, but that's because a lot of the questions I chose have a b value of 1, okay? But I wanted to give you guys the actual formula in case you do encounter some questions where that b value is not 1, then you can just extend the formula to make it work for that case, okay?
I have a question.
Yes.
This is b squared, like for example, like would it be like, would it say on the question like 25 squared, or would it be like something that we could actually like factor to like 5 squared? You know what I mean?
Yeah, that's a good question. So most of the questions are going to have nice numbers. On occasion, you might have like, if you see a 7 where it's supposed to be a squared, that just means a is the square root of 7.
Okay.
Okay, and you would leave it as the square root. You wouldn't turn it into a decimal. You would leave it as the square root.
Okay.
Okay. All right. So this is the formula. So if you see this, then this is the substitution you should make. But I think it's important to talk about why the substitution works, okay? So what we're gonna do is in this little space here, we're gonna show a little bit of a proof in terms of why it works, okay? Now you don't have to do this for every problem, but it's just kind of nice to know, I think, why these formulas work and sort of where they came from, okay? So what we're gonna do is we're gonna take this a over b sine theta, and we're gonna plug that in for the x over here. And so when we do that, we're gonna end up with a squared minus b squared. And then instead of x, I'm gonna put a over b sine theta squared, okay? So once I've made the substitution, there are no more x's in it. And when we do this with integrals, there should be no more x's and no more dx's. So when we make this substitution, we're going to need to make sure we have not only theta in our equation, but d theta as well, okay? So let's do a little bit of algebra here. I've got my a squared minus b squared. And I'm going to take this square and I'm going to square the a, square the b, and square the sine. And so when I do that, I get a squared over b squared sine squared theta. Okay. And then what happens to those b's? Well, this b squared and this b squared, is the morning of technology issues, apparently. Thanks for being so patient, folks. Okay, where were we? So this b squared and this b squared are going to reduce to 1, so we don't need those anymore, okay? And once we've gotten rid of those, well, what do we have? We have a squared minus a squared sine squared theta, Now, when I look at this, I see that both terms have an a squared. So I'm going to go ahead and take that a squared and factor that out, but everything is still underneath the square root. A squared. What's left in the first term once I factor out an a squared?
1 minus sine square.
Yeah, 1 minus sine squared. Good.
It means cos square.
So 1 minus sine squared, we saw that yesterday as one of those Pythagorean identities. We can replace that with cosine squared, okay? So we're gonna get a squared cosine squared theta. Now, are things connected by addition or subtraction? No, they're connected by multiplication, right? And that goes back to that first question. Someone was like, well, can't you just take the square root of each term? And in this case, we can. So square root of a is squared is a. Square root of cosine squared is cosine theta. Okay? So every time you make this substitution, if it's underneath a square root, what you're going to get is a cosine theta. And that's going to allow us to be able to integrate whatever we're working with, okay? So let's see how this applies to example number 1. So in example number 1, I see the integral of 1 over x squared times the square root of 16 minus x squared. Now, in this case, I could use u sub, but only if the outside one was an x, not an x squared. So that squared makes all the difference in the world, and it means I can't use u sub. So now I'm saying, okay, well, this looks a lot like the form I saw above. That 16 minus x squared is really like 4 squared minus x squared. So what I'm going to do is take this part right here, okay? And because this is the first one we're doing, let's kind of write this out to the side. That when I see 16 minus, I'm going to write 1x squared, okay? That's really the same form as 4 squared minus 1 squared x squared, which means that it's exactly like our formula, a squared minus b squared x squared. Now, according to the formula, if you see a squared minus b squared x squared, the substitution you should make is x equals a over b sine theta.
Nice.
If we plug that in for our particular numbers for this problem, we're going to get x equals 4 over 1 sine theta. Okay? Or we could write this as 4 sine theta. All right. So what we're going to do here is go ahead and start substituting. So I have 1 over. Okay, so 1 I don't have to do anything with. Instead of x squared, what should I put?
Whereas equal 16 sine square.
16 sine squared, right? And I think you got that because you said 4 sine theta and you're going to square it. So everywhere I see the x squared, I'm going to put 4 sine theta and I'm going to square it. Okay? So I think I used green. So this is my x, right? Now, I'm going to make that same substitution with the x underneath the square root. So 16 minus 4 sine theta squared. Okay? Now, I have to think about the substitution for dx. Okay? If I write all of this out and I just write a dx at the end, I haven't finished my substitution. So what I'm going to do is go back to my x. Okay. I said that x equals 4 sine theta. What does that make dx?
dx equal 4 cosine theta.
Yeah, 4 stays, right? The derivative of sine is cosine theta. And then we have
d theta.
Good, very good. So what this means, folks, is that everywhere we see the dx, we're going to put 4 cosine theta d theta. So times 4 cosine theta d theta. All right. So before we continue on, I just want everyone to take a look at all the substitutions here and let me know if you have any questions about where these things came
I have a question.
Yes.
Actually, I still don't understand how you got x squared. Like how did you get 4 sine theta for x squared?
So that came from this rule that we said if it looks like this, then this is the substitution we're going to make.
Okay.
Okay. So our job is more about matching the right form. Okay. So I noticed that the problem had 16 minus x squared, which looks like this. A squared minus b squared x squared. So the substitution I want to make then is I take my a, I put it over the b, and then I write the sine theta.
Oh, okay.
Okay?
Okay, perfect. Thank you.
You're welcome. All right. Any other questions about where things came from or where things went? All right. So what we're going to do then is we're going to start to simplify. Okay? So I've got the integral. And I'm going to go ahead and move this 4 cosine theta to my numerator, because 4 cosine theta is the same as 4 cosine theta over 1. And so I can move that to the top of the fraction. And I'm going to keep the d theta at the end. Okay? Now, I know that 4 sine theta, when I square it, I have to square the 4, and I have to square the sine theta. So I get 16 sine squared theta. And again, this came from that 4 sine theta squared. Now, let's see what happens when we expand underneath the square root, okay? So I can write 16 minus 16 sine squared theta. And this gives me 4 cosine theta over 16 sine squared theta. And I'm going to go ahead and factor out that 16. So 16, 1 minus sine squared theta, d theta. Now this 1 minus sine squared, I can replace that with cosine squared theta. And because everything underneath the square root is attached by multiplication, I can take the square root of the 16, which becomes 4, and I can take the square root of cosine squared, which becomes cosine. And then I have my d theta at the end. Okay. So all of this work, our problem got pretty messy. But at this point, it starts to get significantly better. Because check out what I have on the top. I have 4 cosine theta, and on the bottom, I have a 4 cosine theta. So those reduce to 1. So really what I have is the integral of 1 over 16 sine squared theta d theta. Now I'm going to take that 1/16 out to the front as a constant. And at the same time, I'm going to use one of my trig identities to simplify the sine squared. So 1 over sine is the same as which trig function?
Cosecant.
Yeah, 1 over sine is the same as cosecant. So when I have 1 over sine squared, that's the same thing as cosecant squared d theta. Okay. Now, cosecant squared in my integral is actually super nice because the integral of cosecant squared is negative cotangent. That's one of our derivatives, right? The derivative of cotangent is negative cosecant. And so when I integrate this, I'm going to end up with negative 1/16 cotangent theta plus c. So let me zoom back in for a moment and just see, are there any questions so far?
So if we're integrating with respect to x, why do we end up with theta at the end?
Ah, okay. So we made a substitution. It's not unlike we make a u substitution and we're integrating and all of a sudden we have u. All right, so we're using the theta as a substitution to help us be able to integrate. But I think you raised a really good point, which is the answer is not our final answer. And that's why I haven't put a box around it yet, okay? Because since our question was asked with x's, we need to answer with x's, all right?
So you just,
sorry.
So you just did the integral of cosecant squared theta, and that turned into negative 1 over 16 cotangent theta?
Yeah.
All right, cool.
Okay, so the final step here is that we want to make sure our answer is in terms of x and not in terms of theta. And to do that, we're going to go back to our friend, the right triangle, and all we know about SOHCAHTOA. And we're going to use that to help us rewrite our theta in terms of x. So I'm going to do that over here. I'll try and leave better spacing in the next question. I'm going to go ahead and draw a right triangle. Okay. And I'm going to label an angle as theta. And then let's see what information we have. So we said that x is 4 sine theta, okay? Let me write that out over here. X equals 4 sine theta. What that means is that sine theta equals x divided by 4, right? We can just divide that 4 to the other side. But if you think way back to the very first time you heard SOHCAHTOA, you think about what that stands for, sine is the equivalent of the opposite over the hypotenuse. What that means is in my right triangle, the side opposite from theta, I can label as x. And the side opposite, or the side that is the hypotenuse, I can label as 4. Now, if I use my Pythagorean theorem, I can find the remaining side. So that's just going to be the square root of 4 squared, which is 16 minus x squared. Once we've created this triangle, what we can do is use whatever trig function we have to help us plug in with x. So let's go down to the bottom over here. Cotangent, if I think about it in terms of a right triangle, okay, cotangent is the adjacent over the hypotenuse, or opposite. Okay, so this is adjacent over opposite. So all I'm going to do is go to my pink right triangle and take the opposite side, or the adjacent side, sorry, and put it over the opposite side. And that's it. Okay, that's how we get our answer back in terms of x's and not in terms of theta. All right, so let's take a look at this problem, kind of talk through our process again, and then we're going to try that with example number 2. All right, so we started off by looking at, do I see a number squared minus x squared? And once we saw that, yes, you have to end up with an x, okay? It's incomplete if you leave your answer with theta. So we identified that this was a case just like the rule up here. And the rule says that we're going to use a sign substitution, okay? So everywhere that we put our A and our B, that's what we get. We get the 4 sine theta, okay? Now that 4 sine theta, it was also really important for us to make sure that we found our dx, because when we substituted everything in, we needed to substitute in not just my x's, but also my dx. And so what that gave us was a situation where I would say this line is just our substitution line, okay? And from here, we made sure that we substituted in all of our x's as well as our dx. And then, as you move through the problem, we use a lot of algebra to simplify, all right? And we were able to get down to a situation where we got rid of the square root, and we had a term on the top and a term on the bottom that happened to reduce to 1, okay? Now that won't happen in every case, but it is important that we substitute in all the different parts, okay? And then after we took our integral, we had to go back and figure out how do we write our angle in terms of x. And that was all the work in the pink, okay? So we went back to our original x, we set up a right triangle, we found all 3 sides. Now, I tend to do these at the end of the problem, but there's absolutely nothing wrong with doing them as part of your setup so that you know what you're going to substitute in at the very end. And at the end, we end up with this negative 1/16 square root of 16 minus x squared over x plus c. All right? Now, I did see a question that said, could we just substitute in like arc sine of the x? If it's just a theta, yes, but if it is a trig function, then typically we substitute it so it only has the x's, all right, and not another trig function there. Does that clarify that question?
I have one more question. For the sine theta equals x over 4 equals 0 over 4, where did the 0 come from? Is
Opposite.
that just substituting?
Opposite, not 0.
Oh, opposite. Okay.
Opposite.
Thank you.
Yes, that is a Judy ran out of space and didn't want to write opposite. Okay.
I was wondering how you knew it was square root of 16 minus x squared for the other side of the right triangle.
Oh, great question. So if we think back to the Pythagorean theorem, we have a squared plus b squared equals c squared for any right triangle. So if I plug in what I know, I have x squared plus b squared equals 16. So how do I solve for b? I'm going to subtract the x squared and I'm going to take a square root.
Okay, thank you.
You're welcome. All right, so let's go ahead and try example number 2, okay? The setup is going to be very, very similar to example number 1. And again, we'll talk through how we know that they're similar and how we know to choose the sign substitution, okay? So here we go. All right, so I look at this and I see that I have something like a square root of a squared minus b squared x squared. Okay. And I know that when this happens, the substitution I want to make is a over b sine theta. And so when I think about the substitutions here, my a value is not 9, but it's 3. And my b value's not nothing, it's 1. And then I have my sine theta. So we could substitute everywhere we see an x, we can substitute 3 sine theta. Now, while we're here, why don't we go ahead and find our dx as well, okay? So, because I need to substitute not just my x's, but also my dx. So my derivative of 3 sine theta is 3 cosine theta d theta. Any questions on those pieces in the blue? Would we like to set up our right triangle now, or would we like to do it at the end?
I like to just go ahead and do it so I have it.
Okay. So yeah, let's set that up. Might be a better use of the space here anyway. So I've got my theta. I know that my opposite side is going to be x, and my hypotenuse is going to be 3. Okay. And if we use our Pythagorean theorem, that will give us x squared plus b squared equals 9, or b squared equals 9 minus x squared, which makes this side the square root of 9 minus x squared. Okay. So that's excellent. We've done that work. We've put it off to the side, and we know at the end all we need to do is substitute. We don't actually have to come back and do that work after we've done all this really complicated calculus work. Okay. So,
Professor?
yes.
Is the b squared always what's inside, like the function itself?
A lot of times it is, yeah. I think let's try a few more questions before we jump to the always, all right? Okay, so now let's go ahead and substitute everything in, all right? So everywhere I see an x, I'm going to put 3 sine x. So that's going to go here. And then everywhere I see a dx, I'm going to put 3 cosine theta d theta. So that's going to go at the end. So when I substitute, it's going to give me the square root of 9 minus 3 sine theta squared times 3 cosine theta d theta. Okay? So we get 9 minus 9 sine squared theta. And then on the outside, we have 3 cosine theta. Theta. I can factor out a 9 here. And I can make my Pythagorean identity substitution. And then I can take the square root of it. Okay. Now, I do want to point something out here, which is, let me find a good color. Every time we make the substitution and we have a square root, we end up with 3 cosine theta, or like a cosine theta. If I go back up here, I plugged it in and I ended up with my 4 cosine theta. So that goes back to this idea that we showed in our little proof section, which is this substitution is useful because it will always give us a cosine theta. So if you feel like you're doing a bunch of these problems and you're like, oh, I get the pattern now, you can skip right to this a cosine theta part, that's fine. But you need to make sure it's underneath that square root, okay? All right, so where were we? We had our integral of 3 cosine theta, 3 cosine theta. So that's going to give me 9 integral of cosine squared theta d theta. Okay. Now this piggybacks off of what we learned yesterday. All right. So cosine squared theta, when there's no sine theta, I can't use my method of like split it and then use U substitution. This is that sticky case where we have to use that power reducing identity. And so when we substitute that in, we get the 1 plus cosine 2 theta over 2 d theta. And so this is our power reducing identity. All right, so I'm going to factor out that 1/2. I'm going to have a coefficient of 9/2. The integral of 1 plus cosine 2 theta d theta. When I integrate this part, I'm going to need to do that U sub. So that's going to give me the integral of 1 is theta plus the integral of cosine 2 theta is 1/2 sine 2 theta plus c. Now, if you want to, you can substitute at this point. So everywhere we have the thetas, we just need to get it back in terms of x's. But one of the things that we need to be cautious about here is this double angle part, okay? So once upon a time, you also learned about a double angle formula for sine. So that double angle formula for sine.
U sine theta cos theta.
Okay. Now I have a sine theta and I have a cosine theta, which means I can pull the x's right from that triangle that we drew at the beginning, okay? So let's actually do that part first, all right? So I noticed that the 1/2 and the 2 reduced to 1. But let's use our triangle to find an expression for sine theta. So according to this triangle, we can say sine theta is x over 3, or opposite over hypotenuse. So x over 3 is the sine. Times, if we go back up to the triangle, cosine of theta is going to be the square root of 9 minus x squared over 3.
I have a question.
Yeah.
I'm confused what happened in the step before that.
Here?
No, after that?
Here?
Yeah, right here.
Okay, so this is the double angle formula for sine.
Oh, okay, thank you.
No problem. I know. Calc 2 is basically like pre-calc came back and would like, bam, here you go. All those things that you needed to know. Or even going all the way back to trig. All those things are definitely coming back, okay? All right, so we've got our sine and our cosine. Now those, if it has a trig function already, we want to leave it in terms of x's. But someone asked a great question earlier about like, can we just leave it in terms of an inverse angle? And that's fine. So when we just have a theta, the way that we substitute it in, you actually have a little bit of choice. So if I want to find theta, okay, one of the easiest ways to do it is just go back to your original substitution and solve for theta, okay? So if I take x equals 3 sine theta and I solve for theta, let's see what we get. So x equals 3 sine theta. I'm going to divide by 3. And to get my theta by itself, I'm going to need to take the arc sine of x over 3. And the arc sine of x over 3 is what I can put in for theta. Okay. Now, if you wanted to distribute this 9/2 over here and over here, you could certainly do that. All right, and that would give you 9/2 arc sine of x over 3 plus x root 9 minus x squared over 2. All right, because once I distribute this 9
Let's
and those 3's, they reduce to 1. Okay.
Let's see.
Yep. And then we want to make sure exactly we don't forget that plus c at the end. Okay. Whew.
I have a quick question.
What's up?
Why did you want to use a power reducing identity?
Because we don't know how to take integrals of powers of cosine if it doesn't have a sign to use u sub with it.
Okay.
Okay.
So whenever we're left with a sine squared or a cosine squared, we will have to use a power reducing identity in order to get it to a power of 1?
Correct.
Okay.
Yes. Because once we have the double angle, we can use u sub to take the integral. But it's the power that's the tricky part.
Okay.
Great
I have a quick question too. Is there like a list of identities that you need us to know? Do you have a list somewhere?
I'm trying to highlight the ones that are like the ones that tend to come up. So I don't have a list, but I think that's actually a really good studying tool to start to make a list of the identities that are coming up. And then you could put those on your cheat sheet for next week's test.
Okay.
All right. This seems like a good time to take a break. I know that these are sort of really long and complex kind of problems, and we've got 4 more to go through, okay? So let's take a break right now. We'll be back at 10:43, and then we'll get started there, okay?
Professor?
All right, folks, so we're gonna go ahead and get started again. So I'm gonna go ahead and reshare my screen. We're gonna take a look at the second case where we're looking at a situation where a tangent trig function substitution is gonna be useful for us, okay? All right, so here we go. So in this case, we're looking at one very small but significant change. So underneath our square root, we don't have a squared minus b squared x squared, but rather we have a squared plus b squared plus x squared, okay? So this plus sign is important. And so when we're looking at patterns, like I asked you to look for patterns in the beginning, I know I gave you very little direction and it was kind of like, well, what patterns is she looking for? It looks like a bunch of numbers and x squareds, but the signs in between them actually play a really important role, okay? So when we see things that are attached with a plus sign, and then the substitution we want to make is this a over b tangent theta, okay? And so what we're gonna do is we're gonna walk through why that's useful, all right, in this little space over here, and then we're gonna do a couple practice problems. So when we see this substitution, here's why it's useful to substitute in a over b tangent theta for any x's. So we would get a squared plus b squared times a squared over b squared tangent squared theta. And we can see here that those b squareds are going to cancel just like they did in the sine substitution, leaving us with a squared plus a squared tangent squared theta. Now, what's nice about this is, once again, I can factor out an a squared and have 1 plus tangent squared. And what's nice about the plus sign here is the 1 plus tangent squared is one of those Pythagorean identities we talked about yesterday. So everywhere I see a 1 plus tangent squared, I can replace that with secant squared. And now I've created a situation where both of the terms are squared and they're connected by multiplication, which means I can simplify this to be a secant theta, okay? So when we see the plus sign in between, we choose to use this substitution because it gives us a situation with secant that we're going to be able to integrate, okay? So let's go ahead and take a look at example number 3. So I see the 4 plus x squared. It's not a 4 minus x squared, it's a 4 plus x squared. And so what that allows me to do is use the following substitution. I can say that x is going to equal 2 over 1 tangent theta, or more simply 2 tangent theta. And while we're here, let's find our dx. So the derivative of 2 tangent theta is 2 secant squared theta d theta. You can do this next part either at the beginning or the end of a problem, wherever you feel like you'll have more brain space to do that, okay? But what we're gonna do this time, we know that tangent of theta is x over 2, okay? So that we know from our substitution. And tangent is opposite over adjacent. So the side opposite from theta is x, and the side adjacent to theta is 2. And now, when we use our Pythagorean theorem to find the missing side, and some of you have already caught on to this pattern, look at what we're going to get. Okay. And we got that using x squared plus 2 squared equals the hypotenuse squared, and then we just took the square root of both sides, right? So now that we've got everything set up, let's go ahead and make all of our substitutions. So everywhere we see an x, we're going to need to make that into a 2 tangent theta. And everywhere we see the dx, we're going to need to put 2 secant squared theta d theta. I can't stress this enough, how important it is to make all of the substitution. Yes, these problems get longer and messier before they get better, but if you miss a substitution, it becomes like it never ends, okay? Or it doesn't get easier. It just keeps getting worse and worse and worse, okay? So let's make that substitution. 1 over the square root of 4 plus 2 tangent theta squared times 2 secant squared theta d theta. Now, if I want to make this a little bit easier for myself, let's take a look at this structure for a moment. This has some numbers in it, but it is essentially the same as this part, right? 4 plus 4 tangent squared theta is the same as a squared plus a squared tangent theta. And it's under the square root, just like it is in the example we worked above. So it's going to simplify to a secant theta, okay? So I'll write it out for this problem, but in the next problem, we're gonna skip this step, okay? So I have 1 over the square root of 4, 1 plus tangent squared theta times 2 secant squared theta d theta. I end up with 1 over square root of 4 secant squared theta. And then next to it, I have 2 secant squared theta d theta. And I can take this and put it in the numerator. And then the denominator, I can now reduce to 2 secant theta because I took the square root d theta. And so things start to reduce at this point. The 2's are going to reduce to a 1. And one of the secant squareds on the top is going to reduce the 1 on the bottom. And when we do that, all we're left with is the integral of secant theta d theta. Okay. And that is one that should definitely go on that cheat sheet of common integrals that come up. And we saw this one yesterday. It's the natural log of secant theta plus tangent theta plus c. Okay. So that's our substitution part, right? We've got it to an integral that we were able to take, and we got it down to something in terms of theta. And so our last step is now to put back in our x's. So secant is the same as hypotenuse over adjacent, and tangent is the same as opposite over adjacent. Okay, so I'm going to pull the sides from that pink triangle to fill in my answer. So I get the natural log of, let's see, secant is going to be square root of 4 plus x squared over the adjacent, which is 2, plus my opposite side, which is x, over the adjacent side, which is 2, plus c. Right? And that is absolutely fine to leave as a final answer for example number 3. All right, so let's take a look at example number 4, okay? So here's example number 4. I want to give you about a minute or two to kind of start to set things up, see how far you can get in the setup, and then I'll start to put my work up on here, and we'll make sure that we're headed in the same direction, okay? All right, so let's pause for a moment and take a look at what's up on the screen. So we've got x equals our tangent theta, and we knew how to make that substitution because we saw the plus sign in between those. And in this case, a and b are both 1, so we don't really have constants to worry about, but we still have our thetas that we need to be concerned about. And I made the, if you look at the places where we're going to substitute, there are actually 2 places that we need to put the x this time, and 1 place where we need to substitute in that dx, okay? Now that pink triangle looks like we've got our x as our opposite, 1 as our adjacent, and then we're able to find that square root of 1 plus x squared as the hypotenuse. Are there any questions about the setup here? So let's go ahead and substitute all the things in. So the square root of 1 plus tangent squared theta over tangent theta times secant squared theta d theta. Now I'm going to use the work that I did earlier. Square root of 1 plus tangent squared is just going to be secant theta. Now, what does that give me here? Well, that gives me a situation where I can have secant cubed on the top over tangent. And then we can actually take that secant squared and turn it in to a tangent squared plus 1. So we're going to use that Pythagorean identity to have secant theta and then 1 plus tangent squared theta over tangent theta. Now, what I'm going to do here is I'm going to take the secant, I'm going to distribute it to the 1, and I'm going to distribute it to the tangent squared. And at the same time, I'm going to split this one fraction into 2 separate fractions. Okay, so I distributed and I split the fraction. So let's see what we can simplify here. This tangent is going to reduce with one of those tangents. So that second term becomes secant tangent. The first term with the secant over tangent, we're going to rewrite that in terms of sine and cosine and see if we can't simplify that to something that we know the integral of. So one of my go-to techniques is I turn everything into sine and cosine. So instead of secant, I'm going to write that as 1 over cosine theta. And instead of tangent, I'm going to write sine theta over cosine theta. Plus, the second term we said was secant theta, tangent theta, d theta. This first fraction really is the same as 1 over cosine theta times the reciprocal of the bottom. And those cosines go away. And so I end up with 1 over sine theta. But another way to write 1 over sine theta is cosecant theta. Okay, so lots of trig simplifications here. Plus secant theta, tangent theta, d theta. The integral of cosecant, if you look at a table, is the natural log of cosecant theta minus cotangent theta. Plus the integral of secant theta tangent theta is secant. And then we have our plus c, okay? So this one, we used a table to find that, but this one, we just used our knowledge that if we take the derivative of secant x, we get secant tangent. And so if we have secant tangent and we take the integral, we end up with secant. Okay. All right. So I think you all actually made a pretty wise choice to take care of that triangle in the beginning, because as you can tell, your brain gets kind of tired at the end. You're like, I just want to be done with this. I've taken my integral, I must be done. But we do have to substitute back in our x's, okay? So let's see what we have here. I have natural log. My cosecant is going to be hypotenuse over opposite. Cotangent is adjacent over opposite, and secant is hypotenuse over adjacent. And so we're just going to fill in the sides from our triangle. So we'll end up with hypotenuse over opposite minus adjacent over opposite plus hypotenuse over adjacent plus c. All right. If you wanted to, I would say this is not super necessary. Like you get to the end of a problem on a test and you want to leave it like that, that is totally fine. Like everything that you've done, if you wrote it out like this, would be correct and thorough enough, okay? Some folks like to kind of take it a step further and sort of combine fractions if they have a common denominator already, that's fine. And then some people are like, well, why would I write the 1 in the denominator if I don't have to? So maybe dropping that one. But either one of these versions is fine for an answer. All right, how we doing so far out there in the cyber world?
Trying hard to keep up.
Yeah, this section is definitely like, the first 2 days are not so bad, and then this one, it's kind of like there's all this other stuff out there that we have to remember from pre-calc and trig, okay?
What I love about your class is you're always very detailed in how you get to places. My previous teacher was a little confusing. Yours, I can see exactly how you got it, like every step, and like you make it so easy.
I hope that's the case. That's the goal. We want everyone to feel like, you know what, 8 weeks, I'm committed to this, and we're going to do it, and we're going to be successful.
Yes.
All right. So we've got 2 last problems here with our last pattern that we saw at the very beginning, okay? And that is our secant trig substitution. So you'll notice that we're sort of really only working with these first 2 boxes. I included this part in the event that like at some point you might need to do definite integrals. I will not ask you to do definite integrals in this class because I feel like the work we're doing is enough, right? Like we're really working through this kind of stuff. So I just wanted that as like a, in case in the future you ever need to do the definite integrals. But what you'll find with a lot of like really complex integrals is we just really want to get to the integral. We don't really need to necessarily find the area under the curve and get a number as an answer. Okay. All right, so here we go. Last 25 minutes, we got this. So in the event that you see a subtraction sign, okay, you might wonder, how am I going to know if it's secant or sine? So the minus sign tells you it's not tangent. But the other indicating factor here is that the x squared comes first. When the x squared comes first, it's going to be secant. Whereas in our sine substitution, the x squared comes second, like after the minus sign, it's not a secant, okay? So when the x squared is before the minus, it's a secant, but if the x squared is after the minus, it's a sine substitution, okay? And again, for most of these problems, I'm not giving you a value for b. I will in example number 6, just so we try one to see that it's just like a few extra constants here and there. But I really want us to get the hang of like how to do this just when b is equal to 1. All right, so like the other ones, let's kind of see why this substitution is useful for us, right? So we're gonna plug in everywhere I see the x, I'm gonna put in a over b secant. And since I'm squaring it, I'm gonna go right ahead and square the a, square the b, and square the secant. Then I'm not gonna forget that minus a squared there. And like all the other problems we've seen, the b squareds are gonna reduce to 1. And I'm going to be able to factor an a squared out of both terms. And this is a version of one of our Pythagorean identities. And we can say that this is a squared tangent squared. And the beauty of that, that is different from our initial, is that this, we can take the square root of both terms because they're connected by multiplication. And so in this case, a nice shortcut that we can use is when we see that square root of x squared minus a number, we can immediately substitute in a tangent theta, okay? So let's see how that looks in example number 5. So I see the x squared before the minus sign, so I'm thinking secant, not sine. So I get 3 secant theta, and then I'm going to find my dx at the same time. So I'm going to get 3 secant theta, tangent theta, d theta. Okay. And let's go ahead and set up that triangle so we know at the end what our substitutions are going to be. We know that secant is x over 3, which is the hypotenuse over the adjacent. So x and 3. And then, yep, to all those folks who are like, can I always use that f of x as that missing side? Seems like the answer to that is yes, right? We've been able to do that for every problem that we've seen. So really good job picking up on that pattern. Okay, so now let's substitute in everything. Nine secant squared theta minus 9 over 3 secant theta times 3 secant theta tangent theta d theta. Now, this is under square root, and it looks pretty much like this. So instead of working out all these simplification steps, I know it's going to simplify to 3 tangent theta. So this was just kind of saying, hey, I've kind of seen this pattern a few times, and I know if it's underneath the square root that I can just kind of simplify that right away, okay? And now let's go through and maybe think about what we can reduce and what we can't. So I hope that we all see this 3 and that 3 could reduce, right? And then what else reduces here?
Secants?
Yeah, the secants reduce. What about the tangent?
squared.
It's going to be tangent squared. Good. Okay. So when you're simplifying, it's really important that you make sure you know, like, it only reduces if one's on the top and one's on the bottom. But if they're next to each other, it's going to turn into a squared situation. Right? So when I rewrite this, I'm going to end up with 3, the integral of tangent squared theta d theta. And this is one of the cases we saw from yesterday where the power of tangent is even. And so in that case, we turned it into a secant squared theta minus 1. Okay. And this worked out really nicely because we know the integral of secant squared, but we don't know the integral of tangent squared. Okay. So the integral of secant squared is tangent theta minus the integral of 1 is theta. And then because we already set up our triangle, we just need to plug things in. So we're going to get 3, and tangent is opposite over adjacent. So that over 3 minus, you could put whatever you want for theta. Again, I think I like to go back to whatever I said was x and solve for theta. And so that would give me the inverse secant of x over 3. Okay. But for example, it would not be wrong to write the inverse cosine of 3 over x. Like, that's another option. That's totally fine. So if you don't like secant, but you think cosine is like easier for you to think about, you could do that. You could also do inverse sine of root x squared minus 9 over x. That would be fine. So you have a lot of options to choose from on how you write your theta. It just has to be correct, like it has to line up with your triangle, but otherwise you can choose from any of the 6 trig functions and it would be fine, okay? If you wanted to distribute that 3, then this first term would become x squared minus 9, but the second term would stay as 3 inverse secant of x over 3. Okay, so you can't cancel this 3 and that 3 because like the x over 3 is being inverse secanted, so you can't cancel it out. So, not so bad, okay? Not so bad. I think once we start to do a few of them, the patterns definitely start to sink in, and it sounds like from hearing a lot of your participation that we are picking up on these patterns, and that's really good, okay? Now, I would really encourage you when you prepare for next week's exam, what's really important here is for you to practice making these decisions on your own. Okay, so as you're studying, whether you're studying by yourself or studying in a group, you really want to think about, okay, this is the rule. Just because someone else says, oh, this is the rule we need to use, you make sure you know why you're choosing that rule, right? Like if someone says, oh yeah, this is a secant substitution, make sure you follow that up with either ask if you don't know why, or be like, oh, right, because it's the x squared minus something, right? So like those kinds of conversations are actually really, really valuable to studying. I think more so than sitting and trying to do like 20 of them without really knowing why you're making certain decisions, okay?
I have a question about the exam.
Yeah.
For the exam, like how is it gonna work? Like, are we gonna have to work on it at a time, like there's a time limit, and are we gonna have to use the Canvas only, or are we able to like use, like upload it, then use our notebook to do the answers and then take picture and then upload it like as a quiz, or like?
Great question. How about let's finish this problem. If we have time, I'll either talk about it right at the end, or tomorrow when we start class, I'll make sure to talk about that exam, because we're only out, so I want to make sure we're preparing mentally for that. Okay? Okay.
So this type of question is not going to be in the test, right? This this formula specifically.
Why not?
Oh, I thought you said we weren't going to do these type of problems or this type of problem. Or maybe I heard wrong.
Yeah, maybe. Sorry, I say so many things. I didn't mean to say that. No, I think what I was saying is that when we're looking at like this b value, most of the problems we're working with has b equal to 1. That's the kind of question I'm going to be looking for.
Okay. Thank you.
All right, so this is an example maybe of what I was talking about. Okay, so in this case, b is not equal to 1. I wanted us to try 1, but I think that when b is not equal to 1 is not a question that I would ask on a test. Okay, but the other questions are fair game. Like this topic is fair game. All right, so let's do this last example. We've got a square root. We've got x squared minus something. So I know I'm doing a secant substitution. In this case, there is a b value. So my substitution is going to be a over b secant theta. All right, that's the only difference. Now you've got some fractions instead of whole numbers. Everything else that we're going to do, all the other substitutions, writing that triangle, everything else is going to be the same. So while we're here, let's find our dx. And let's draw our triangle. And let's see. I know that we have 5x over 2 equals secant theta. And we know that secant is the hypotenuse over the adjacent. So my hypotenuse is 5x. My adjacent is 2, which is perfect because that square root that was in my problem is my missing side. Good, okay? All right, so now let's make our substitutions. We just have to be a little bit more careful because we've got some fractions going on here. So this becomes 25, 2 over 5, secant theta squared minus 4 over, I need to put an x here too, times dx okay. Now again, this top part here is underneath a square root, so I know it's going to simplify to a over b, or a tangent theta, okay? So I don't need to do the algebra there. I know that it's going to simplify. So what do we get here? We end up with 2 over 5 tangent theta over 2 over 5 secant theta times 2 over 5 secant theta tangent theta d theta. And like a bunch of the other problems, this is the messiest step. Things start to cancel. So 2/5 and 2/5, secant and secant, right? And so we end up with 2/5, the integral of tangent squared theta d theta, which is perfect because we can use that same substitution we did earlier, secant squared theta minus 1 d theta. And secant squared, we know that integral is tangent theta, and we know the integral of 1 is theta. And all we're going to do now is plug back in our x's that we got from our triangle at the beginning. And so that's going to give us 2/5. Tangent is going to be opposite over adjacent minus, again, you could write the theta a number of ways. I tend to prefer whatever I started with. So I have arc secant of 5x over 2. But you could use arc cosine, arc sine, arc tangent, any of those you could, okay? And after that, we just need to have our plus c. And that's it. Okay, so as messy as these problems get, there is definitely a pattern sort of as you go through a bunch of these problems, okay? I definitely think that they're challenging, but again, the ones where the b value is not equal to 1, I'm not going to ask on a test, but like numbers 1 through 5 would certainly be fair game, okay? And last but not least, at the bottom here, I just made like a little summary table here so that you can kind of have it all in one place as you're studying. And again, those limit assumptions, we're not really worried about those for this particular course, but I wanted to have them there in case you need them for some future course, okay? So that's it in terms of the content for today. And I see a couple questions in here and I just want to answer those. So, all right, so in these last 5 minutes, let's kind of talk about exam number 1. How many questions will be on the exam? I believe there are usually anywhere between 10 and 15 problems on an exam. There will not be a practice exam available. In terms of questions, you should find that they are pretty aligned to the quizzes as well as to the work that we do in class, okay? So my goal between the quizzes and the work that we're doing in class, like the lecture stuff, is that together they're really preparing you for the kinds of questions that you'll be expected to answer on the test, all right? I do want to make sure that we know how to make decisions. So there will be parts to the exam where I ask you to explain your decision making. Like, how did you know to make a secant substitution? And you don't have to write like a whole novel on it. You can just say, well, it's like x square root of x squared minus a squared. That's totally fine, okay? Or how do you know that you can use u substitution? And your answer could be as simple as, I see this function and I see part of its derivative, okay? Or how did you know to use integration by parts? You know, so think about those as you're working on studying for the test, that we are gonna be, you're definitely gonna be asked to explain your thinking instead of just doing the problems, okay? Okay, so an error in the calculator, let me check that later and get back to you. That is certainly possible that there's an error somewhere. Are you talking about number 6 specifically? Okay, I hope it's for number 6. I'll check that one over. Okay, so for the exam, I was, you know, planning for the class and thinking, all right, 6 hours is sort of a reasonable amount of time. But one thing that I talked to a bunch of students before the class started, and I know that there are definitely a significant number of you who are working, and if not working part-time, working full-time. So what I'd like to do is actually use 24 hours to sort of accommodate everyone's work schedules. I know that, you know, it's never really ideal to work full time while you're taking a course as rigorous as this, but I also know we don't really have a lot of choice in that. So I am going to change that. I'll change that on Canvas as this, and on the syllabus as well. So the way things work for a test. So at 9:30 on test day, then the test will be available to you. That means that you have until 9:30 the following morning to submit your exam, okay? I took a course this last semester. My professor did that for me, or well, not just for me, but for the whole class. And I found that incredibly helpful, not because I needed 24 hours to do the exam. So I'm not writing a 24-hour exam. Let's just be clear about that, okay? You should not take 24 hours to do this exam. You should still have time to eat and sleep and do all the other things in your life and take the exam. But with that, what I found helpful was I could kind of work through the things I felt confident on, think about like the other ones, and then go back and work on them later, okay? I do want to say this though, if we encounter a situation where there is a lot of cheating happening, and I can tell when folks are cheating on their exams, okay? So if there's a lot of cheating happening, then we will go back to a shorter time period. I want to be able to respect how crazy it is for everyone right now. I really do. But I also don't want to do that at the cost of the integrity of the grades in this class, okay? So even though you have 24 hours, please use your time before that to prepare a cheat sheet. That means you don't need your notes because you have everything on those 2 sheets, okay? You're gonna submit this cheat sheet on the exam too. I wanna see what kind of stuff people is putting on there, what's helpful for you, what's not helpful, okay? So whether or not you use one, I ask you to submit one with your exam. And I definitely have had folks like do some work and I'm like, where did they get this formula from? But it's on their cheat sheet. So for me, that brings me just a little bit more comfort that you're not using external resources during the time of the exam. Other than that, make sure that you submit your exam by the time, okay? So if an exam is on Wednesday next week, that means we do not meet for class, but at 9:30 on Wednesday morning, you can access the exam, and then you must submit that by 9:30 Thursday morning, okay? I had a few students last semester who thought that the test opened on different days, and they went in and the test had already passed. So I would really encourage you to make sure to stay on top of the schedule and make sure that you're reading any announcements that kind of come out. What would you be using Euler's formula for? Okay, well, Alberto, when you get back to me on that, I'm just curious what you're going to be using it for. As far as putting examples on your cheat sheet, you can 100% put examples on your cheat sheet. I know that when I was taking, you know, exams in college that I was allowed to use a cheat sheet for, I found it way more helpful to have like, maybe not even examples, but sort of the steps written out. So I kind of knew like how to approach a problem. And yeah, I think I would definitely be open to that. I think one thing to just be careful about, I never want to put a limit on people's creativity in terms of problem solving. I think some of you out there are really, really strong problem solvers. But I would encourage you to kind of try and stay within the realms of what we learn in this class, because to me that is like, there's sort of, yes, there might be better, faster ways to do things, but there are certain things that I'm looking for mastery of in this class, if that makes sense. So like, I want to know that you know how to solve it this particular way because that's what we're covering, even though there might be another way that's maybe easier or more streamlined. So maybe we could kind of keep things to like what we're learning in the context of this class. yes, that channel is definitely a great one. And then Patrick JMT has a pretty good one as well. And then I think someone had mentioned Nancy Pie is a great one. There's so many great YouTube channels out there. So definitely take advantage of those, okay? And I love that you guys are sharing resources with each other. I know it must be hard to not really know who else is in the class, but I hope you continue to do that. All right, so I want to respect your time. I know we're a couple minutes over, so thank you for that. But if you have any other questions, feel free to stick around. I'm just going to stop my share and I'm going to stop the video. But if you have any questions about the quiz, you can hang around for a little bit and I'm happy to go over some of those, okay?
Thank you.
Bye.
Thank you.
Thank you. Have a good one.
Thanks, you too.